piano makers and furniture craftsmen built the fastest bomber of World War II. The Royal Air Force rejected it 3 times. The British Minister of Aircraft Production nicknamed it Freeman's Folly, a joke, a waste of resources. Senior military officials said it would never survive combat. Aviation experts declared the concept fundamentally flawed. And then it outran every metal fighter in the sky at 439 miles per hour, made almost entirely of wood. This isn't science fiction. This is the de Havilland Mosquito, the wooden wonder that proved every expert wrong. Here's what makes this story unbelievable. While other nations built bombers from tons of aircraft-grade aluminum, Britain built theirs from 6 tons of wood held together by over 50,000 brass screws. While competitors needed 60 to 80 days to manufacture a single bomber, British workshops completed a Mosquito in just 32.6 days on average. While heavily armed metal bombers carried crews of 6 to 10 men, this wooden aircraft carried 2 and no defensive guns whatsoever. Its only defense? Pure speed. November 25, 1940, Hatfield Aerodrome, England. 10:47 a.m. Geoffrey de Havilland Jr. climbed into the cockpit of a bright yellow prototype that, according to official military doctrine, shouldn't exist. 2 Rolls-Royce Merlin engines, a frame constructed from Canadian birch, Ecuadorian balsa, and English ash, 0 weapons, 0 armor plating. He pushed the throttles forward. The wooden aircraft lifted off the grass runway. 24 minutes later, everything changed. That first flight reached 220 miles per hour immediately. Within weeks, it hit 392 miles per hour at 22,000 feet, faster than the Supermarine Spitfire, Britain's legendary fighter that had just won the Battle of Britain. By 1943, a modified version touched 439 miles per hour at 29,000 feet, making it one of the fastest operational aircraft in the world. By war's end, 7,781 of these wooden marvels rolled out of factories, workshops, and cottage industries across Britain, Canada, and Australia. Furniture companies built fuselage sections. Piano manufacturers crafted wing spars. Small family businesses assembled tail sections in workshops that had never built an aircraft before. Hermann Göring, Reichsmarschall of the Luftwaffe and commander of all German air forces, watched Mosquitoes strike targets across occupied Europe with near impunity. He reportedly said, "It makes me furious when I see the Mosquito. I turn green and yellow with envy. The British, who can afford aluminum better than we can, knock together a beautiful wooden aircraft that every piano factory over there is building, and they give it a speed which they have now increased yet again." Even Germany's leadership recognized they'd been outsmarted by furniture makers. But the real engineering brilliance wasn't just the speed. It was how they solved an impossible problem that every other aviation engineer said couldn't be solved: building a combat aircraft from non-strategic materials that could outperform purpose-built metal fighters. This is the story of unconventional thinking, rejected innovation, and the engineering breakthrough that changed aerial warfare forever.
September 1939. Britain declares war on Germany with a crippling disadvantage. The RAF's bomber fleet consisted of slow, heavily armed aircraft like the Vickers Wellington and Bristol Blenheim. These bombers carried defensive gun turrets, armor plating, and crews of 4 to 6 men. The Wellington could manage 235 miles per hour. The Blenheim, slightly faster at 266 miles per hour, but still easy prey for German fighters. The mathematical reality was brutal. Every gun turret added weight. Every defensive weapon added drag. Every additional crew member required space, equipment, oxygen systems, and armor protection. The bombers were trying to fight their way through enemy airspace, and they were losing. Losses were catastrophic. During early bombing raids, some squadrons lost 20% of their aircraft in a single mission. The Luftwaffe's Messerschmitt Bf-109 fighters capable of 354 miles per hour, hunted British bombers like wolves picking off wounded elk. The Air Ministry issued specification P-1336, demanding a twin-engine medium bomber carrying 3,000 pounds of bombs for 3,000 miles at 275 miles per hour. Aviation companies responded with bigger engines, more guns, additional crew members, making the aircraft heavier, slower, more vulnerable. Meanwhile, Britain faced another crisis: material shortages. Aircraft-grade aluminum was strategic material desperately needed for fighters like the Spitfire and Hurricane defending British skies. Steel went to ships, tanks, and artillery. Every ton of metal allocated to bombers meant less for defensive fighters. And then there was manufacturing capacity. Britain's aircraft factories were operating at maximum capacity, employing skilled metal workers who couldn't be replaced quickly. The aviation industry couldn't expand fast enough to build the bomber fleet Britain needed. Geoffrey de Havilland saw these problems differently. What if the solution wasn't adding more weapons, but removing them entirely? What if instead of trying to fight through enemy defenses, an aircraft simply outran them? What if that aircraft could be built from non-strategic materials using workers who weren't specialized aircraft technicians? It was a radical concept that challenged every assumption about bomber design, and almost nobody believed it would work.
The engineering breakthrough came from an unlikely source: furniture construction. De Havilland had experience with wooden aircraft construction from their DH.88 Comet Racer and DH.91 Albatross airliner. But the Mosquito would take this technology to unprecedented levels. The key innovation was the composite sandwich construction technique, a method that sounds simple but required extraordinary precision. Here's how it worked. Thin sheets of Canadian birch plywood formed the outer skin. The core consisted of 3/8 inch thick Ecuadorian balsa wood. Another layer of birch plywood formed the inner skin. These three layers were glued together using a casein-based adhesive derived from milk protein, then pressed into massive mahogany molds shaped like half fuselages. The genius was in the engineering properties. Balsa wood has an exceptional strength-to-weight ratio. Pound for pound, it's as strong as steel in compression. The birch plywood provided tension strength. Combined in a sandwich, these materials created a structure stronger and lighter than many metal alternatives, while being far easier to manufacture. The fuselage was built in two halves using heated concrete molds. Steel band clamps tightened by turnbuckles compressed the layers together, forming the curved shape. Each half fuselage was essentially one large molded piece, with internal equipment installed before the halves were joined together. This eliminated thousands of rivets and assembly steps required for metal aircraft. But what they didn't know was that this construction method would create unexpected advantages. Wood absorbed vibrations better than metal, making the aircraft more comfortable to fly. It was naturally radar absorbent, giving primitive stealth characteristics. And critically, battle damage was easier to repair. Bullet holes could be patched with simple woodworking tools, rather than requiring specialized metalworking equipment. The wings used a similar sandwich construction, but with additional complexity. They incorporated Sitka spruce from North America for the main spars, the structural backbone carrying flight loads. Douglas fir reinforced stress points. English ash provided impact resistance. Walnut created smooth aerodynamic surfaces. The real breakthrough came when engineers calculated production requirements. Each Mosquito required approximately 6 tons of wood and over 50,000 brass screws. A typical bomber required 10 to 15 tons of aluminum, thousands of hours of precision metalworking, and specialized tools that could take months to acquire. However, the biggest challenge was still ahead: convincing the Air Ministry that a wooden bomber without defensive guns could survive combat.
July 7, 1938, Geoffrey de Havilland wrote to Air Marshal Wilfred Freeman with a proposal that would be rejected repeatedly over the next 2 years. The concept? A twin-engine bomber constructed primarily from wood, carrying a 2-man crew with 0 defensive armament. Top speed estimated at 400 miles per hour at 24,000 feet altitude. The speed would be its only defense. The Air Ministry's response was swift and dismissive. Fighter Command wanted heavy bombers with maximum defensive firepower. The prevailing military doctrine demanded aircraft that could fight their way through enemy territory. An unarmed bomber contradicted everything the RAF believed about aerial warfare. Lord Beaverbrook, Minister of Aircraft Production, gave it a mocking nickname, Freeman's Folly, a reference to Air Marshal Freeman's seemingly misguided support for this wooden fantasy. In 1938, the proposal was formally rejected. In early 1939, rejected again. De Havilland persisted, refining designs, producing performance calculations, arguing that wooden construction would free up strategic aluminum for fighters while allowing rapid production using non-traditional labor. Then May 1940 brought disaster. Germany's blitzkrieg smashed through France. The British Expeditionary Force evacuated from Dunkirk. Suddenly, Britain stood alone, desperately needing every fighter to defend against invasion. Lord Beaverbrook issued orders: concentrate production on 5 existing aircraft types only. Everything else, including the DH-98 Mosquito project, was to stop immediately. Freeman received the order, but deliberately didn't pass it on to de Havilland. This act of bureaucratic insubordination kept the project alive during Britain's darkest hour. Work continued in secret at Salisbury Hall, a secluded manor house outside London where a small design team operated away from oversight. But this was only the beginning of the struggle. Even after the prototype proved itself, skepticism remained. Military planners couldn't accept that speed alone could provide adequate defense. They demanded gun turrets, additional crew members, armor plating, modifications that would have destroyed the aircraft's performance advantages. What finally changed their minds was a single test flight that made believers out of skeptics.
January 16, 1941. RAF Boscombe Down, Wiltshire. The Yellow Mosquito prototype, designated W4050, sat on the runway facing an unusual opponent. Parked beside it was a Supermarine Spitfire Mark II, the RAF's frontline fighter, the fastest operational aircraft in Britain's inventory, the symbol of the Battle of Britain's victory. The test parameters were simple: a straight race from 6,000 feet altitude. The Spitfire, a single-engine fighter weighing 6,785 pounds with one Merlin engine producing 1,175 horsepower. The Mosquito, a twin-engine bomber weighing 14,150 pounds with 2 Merlin engines producing 2,560 horsepower combined. Engineering calculations predicted the Mosquito would be marginally faster, perhaps 20 miles per hour advantage. It had twice the surface area and over twice the weight of the Spitfire, but also twice the power. Basic physics suggested modest superiority. Both aircraft took off. At 6,000 feet, they leveled out for the speed run. The Mosquito didn't just beat the Spitfire, it humiliated it. The wooden bomber pulled away from Britain's fastest fighter as if the Spitfire was standing still. Final results: Spitfire maximum speed at 6,000 feet, 360 miles per hour. Mosquito speed, 392 miles per hour. A 32 miles per hour advantage. But the real breakthrough came weeks later during high-altitude testing. At 22,000 feet, the Mosquito maintained 392 miles per hour, while the Spitfire could only manage 360 miles per hour at 19,500 feet.
The wooden bomber was faster at every altitude. The numbers silenced the skeptics. Initial handling reports from test pilots described light and effective aileron control and pleasant handling characteristics. Maximum ceiling reached 34,000 feet. Rate of climb hit 2,880 feet per minute. The performance exceeded metal bombers in every measurable category. Orders flooded in. The Air Ministry authorized mass production on June 21, 1941. Fighter Command wanted a night fighter version with radar equipment. Bomber Command demanded long-range reconnaissance variants. Coastal Command requested maritime strike capabilities. The Mosquito's versatility solved another engineering problem. Traditional aircraft development required separate designs for different roles. One aircraft for bombing, another for reconnaissance, another for fighting. The Mosquito's basic airframe could be modified for multiple missions by changing nose configurations and equipment packages. This manufacturing flexibility meant production lines could adapt quickly to changing operational requirements. But the breakthrough in speed was only part of the engineering triumph. The real innovation was how they built thousands of these aircraft without disrupting Britain's critical metal aircraft production.
The production strategy was revolutionary. Decentralized manufacturing using non-traditional labor. More than 400 British companies contributed to Mosquito production. Furniture manufacturers built fuselage sections. Piano makers crafted wing spars. Small family workshops produced control surfaces. Cabinet makers assembled tail sections. This cottage industry approach distributed production across Britain, making the supply chain resilient to German bombing while tapping labor pools unavailable to traditional aircraft factories. The construction timeline per aircraft was extraordinarily fast. From raw materials to completed aircraft, approximately 32.6 days on average during peak production. This speed resulted from the modular construction method and simplified assembly process. Here's how the timeline worked. Week 1 involved cutting and preparing wood components. Week 2 focused on gluing and pressing major assemblies in heated molds. Week 3 covered assembly of fuselage halves, wing construction, and systems installation. Week 4 involved final assembly, engine installation, and systems testing. By week 5, the aircraft underwent flight testing and acceptance checks. Compare this to a metal bomber like the Handley Page Halifax, which required 60 to 80 days from start to completion, with far more complex manufacturing processes requiring specialized metalworking tools and skilled tradespeople. The material supply chain demonstrated remarkable global coordination. Ecuadorian balsa wood arrived by ship from South America. Canadian birch came from Quebec forests. Sitka spruce from the Pacific Northwest of North America. Australian coachwood substituted when Canadian birch supplies ran short. English ash from local woodlands. This international supply network kept production flowing despite shipping challenges. One concern emerged early: balsa wood shortages. Ecuador was the primary source, and submarine warfare threatened supply lines. Engineers calculated that if balsa wood supplies dried up completely, the entire program might collapse. Fortunately, sufficient stockpiles and protected shipping routes maintained adequate supply throughout the war, though supplies remained tight at several points. The decentralized production created quality control challenges. Components manufactured in different workshops needed precise dimensional accuracy to fit together during final assembly. De Havilland solved this with standardized molds and jigs distributed to subcontractors. These precision tools ensured that a wing spar made in Yorkshire would perfectly mate with a fuselage half built in Kent. By war's end, production reached impressive numbers. Total Mosquito production, 7,781 aircraft built between 1940 and 1950. Of these, 6,710 were delivered during wartime. Production facilities operated in Britain, Canada, and Australia, with Canadian factories alone building 1,032 aircraft. But would this wooden wonder actually survive combat. The final test came during one of the war's most daring missions.
February 18, 1944. Operation Jericho. Amiens prison, German-occupied France. French resistance members and Allied agents sat in prison cells awaiting execution by the Gestapo. Intelligence indicated that 120 prisoners would be shot within days. A desperate request reached RAF headquarters: destroy the prison walls to allow escape. The challenge seemed impossible. The prison sat in the center of Amiens, surrounded by civilian buildings. Guards' barracks stood adjacent to prisoner blocks. The walls were 3 feet of solid stone. Bombing from high altitude would cause massive civilian casualties and likely kill most prisoners. The mission required surgical precision at extremely low altitude. 19 Mosquitoes from No. 140 Wing received the assignment. The plan: approach at treetop height, drop 500-pound bombs with delayed fuses to breach the outer walls, strike the guards' barracks to create chaos, then destroy the prison administration building. All of this at 60 feet altitude while traveling at 300 miles per hour. At noon, the Mosquitoes swept in over the French countryside. The wooden construction created less vibration during low-level flight, getting pilots better control for precision bomb placement. The first wave dropped their bombs directly against the outer prison wall. Massive explosions punched a hole 50 feet wide through 3 feet of stone. The second wave struck the guards' barracks, destroying German quarters and creating pandemonium. The third wave demolished the administration building, destroying files and adding to the confusion. Of the 832 prisoners held at Amiens, 258 escaped through the shattered walls, including 79 resistance members and political prisoners scheduled for execution. The cost: 102 prisoners killed by bombing, 74 wounded, and 2 Mosquitoes shot down. The operation validated every design decision. The wooden construction allowed low-level flight through turbulent air. The speed made them difficult targets for anti-aircraft guns. The precision bombing demonstrated capabilities no heavy bomber could match. The mission became legendary, proof that unconventional engineering could accomplish impossible objectives. Even Germany's leadership recognized the engineering brilliance they faced daily in the skies over occupied Europe.
But the story doesn't end with combat success. Engineers continued pushing the Mosquito's performance boundaries. December 1943. The prototype W4050, now extensively modified, underwent high-altitude testing with 2-stage, 2-speed supercharged Merlin 77 engines. These engines maintained full power at altitudes where standard engines gasped for oxygen. At 29,000 feet altitude, W4050 achieved 439 miles per hour in level flight. This made it faster than virtually every fighter aircraft in operational service, German, British, or American. The Wooden Wonder had become one of the fastest combat aircraft in the world. This speed resulted from continuous aerodynamic refinement. Engineers eliminated the tailplane buffeting problem that plagued early prototypes by adding wing root fillets and extending engine nacelles. The wingspan increased from 54 feet 2 inches to 59 feet 2 inches for high-altitude variants, improving lift characteristics at extreme altitudes. The performance specifications became legendary. Maximum range, 2,450 miles. Service ceiling, 37,000 feet. Rate of climb, 2,880 feet per minute. Bomb load capacity, 4,000 pounds. The Mosquito could carry the same bomb load as a B-17 Flying Fortress to Berlin and back, but do it faster, higher, and with a 2-man crew instead of 10. The lowest loss rate of any bomber in RAF Bomber Command during the war belonged to the Mosquito. Its combination of speed, altitude capability, and maneuverability made it nearly impossible to intercept.
German night fighters that devastated heavy bomber formations could rarely catch a mosquito. The wooden construction proved its durability in ways engineers hadn't anticipated. Aircraft returned from missions with battle damage that would have doomed metal aircraft. One Mosquito landed safely after a German fighter's cannon shells blew a 3-foot hole in the wooden fuselage. The flexible structure absorbed the impact without catastrophic failure.
The Mosquito flew until 1963, outlasting most metal aircraft of its generation. Its engineering principles influenced post-war aviation in unexpected ways. The composite sandwich construction technique, pioneered for the Mosquito, became the foundation for modern composite materials used in everything from Formula One race cars to commercial aircraft. Today's Boeing 787 Dreamliner uses carbon fiber composites in sandwich construction, a direct descendant of the wooden technology developed at Salisbury Hall in 1940. The decentralized production model demonstrated that complex technology could be manufactured by distributed networks of smaller producers. This concept influenced modern supply chain management and just-in-time manufacturing systems used by industries worldwide. The speed as defense philosophy, validated by the Mosquito, influenced Cold War strategic bomber design. The American B-58 Hustler, British V-bombers, and Soviet Tu-22 all embraced the concept that speed could substitute for heavy defensive armament. Perhaps most importantly, the Mosquito proved that unconventional solutions to engineering problems could outperform traditional approaches. When everyone else added weight in weapons, de Havilland subtracted them. When others demanded metal, he used wood. When conventional wisdom said impossible, he asked, why not? Today, only 3 airworthy Mosquitoes remain in existence, 2 in the United States, 1 in Canada. But their legacy lives on in composite materials, distributed manufacturing, and the engineering philosophy that sometimes the most elegant solution comes from questioning fundamental assumptions. The wooden wonder that aviation experts rejected became one of history's most versatile combat aircraft, proving that 6 tons of wood and 50,000 brass screws, assembled in 32.6 days by furniture makers and piano builders, could outperform the most advanced metal bombers of its era. From a rejected design to 439 miles per hour, from cottage workshops to 7,781 aircraft, from Freeman's folly to Hermann Göring's envy. The de Havilland Mosquito solved an impossible engineering problem not by adding complexity, but by eliminating it. Not by following conventional wisdom, but by challenging every assumption. Not by demanding strategic materials, but by using what others considered obsolete. The next time you face an impossible engineering challenge, remember the wooden wonder. Sometimes the solution isn't building stronger, it's building smarter. Sometimes speed beats armor. Sometimes wood beats metal. Sometimes the most revolutionary innovation comes from questioning why things have always been done a certain way. If you enjoyed this deep dive into technical problem-solving brilliance, subscribe for more stories of how technical problem-solving changed history. Next week, we'll explore another communication breakthrough from World War II, how the British broke the Enigma code not through one genius moment, but through industrial-scale engineering that built machines to defeat machines. Hit that subscribe button, and remember, engineering isn't about following rules, it's about solving problems. Sometimes with 6 tons of wood, 50,000 brass screws, and absolute determination to prove the experts wrong.